question in English. Okay, so please, Irma, you're the first here right next to me in my screen. Give me a number. I will not volunteer you just yet. Just give me a number and then.
6.
Okay. Murakami. So please, you and your team start presenting. Share your screen and you can start with the first part of the presentation for the homework. We said that we will investigate the root heuristic criteria, and the first point was basic assumptions for the root heuristic criterion and how to make the root heuristic table. So you have the presentation, or someone in your team. Okay. Who else is with Murakami in the team?
Me, teacher. But in fact, we weren't able to finish the presentation.
You weren't able to finish. Okay. Someone else can take that point, or we go to the next point. If some other team can take it, it's good for everyone. Remember that all the group will have the same grading in here.
Us.
Okay, please go ahead, Juan Pablo.
Okay, so according to, can you hear me?
Yes, I can hear.
According to where we investigated the Hurwitz criterion, it's a way to see if a system is stable or unstable. And to do that, we create a table called a root array. And by checking the signs of the first column, we can determine if the system is stable or unstable. And also by checking the sign changes, we can see the number of poles.
Okay. Is it possible to know where the poles are located using this tool?
Oh yeah, and it was by counting the number of sign changes.
Yeah,
those are the ones that are in the right-hand plane.
Okay, but we cannot know exactly where they are, right? You can only know how many you have in the right side, and by consequence, you also know how many you have on the left. But yeah,
yes,
that's correct.
And so this is our first example. It's a 6th order example. So to create the RH table, we have to take the coefficients by skipping 1 in the first row. We take the 1, which is the coefficient of s to the 6. Then we skip 1, the coefficient of s to the 5. We skip it, and we choose the one of s to the 4, which is 11. Then we also skip 1. We get the 7, and lastly the 0.5. And for the second row, we do the same with the coefficients that we didn't choose, which are the 5, the 12, and the 2. And for the last one, we just write down a 0. Another way of seeing it is just going in this order, like 1 down, 1 to the diagonal, 1 down, 1 to the diagonal, to write the coefficients. So for the s to the 4, what we need to do is, there are some formulas for this, but I prefer to see it like this. We're gonna take the coefficient in this position, and we're gonna multiply it diagonally to the right side. Yeah. Then we're gonna subtract the other diagonal, the 1 times the 12, and we're gonna divide everything times the 5, which is our initial value. And as you can see, the result we get is 8.6. Now for the next values, we do the same thing, but we ignore the values on the middle, and we start doing it with the values that are far far to the right until we reach the end of the table. And basically we keep repeating the same process until the, oh, sorry. We keep repeating the same process until the table is completely filled. And as you can see here, in this case, we take these values here, and which are these ones. And if you see, all of them are positive, so this system is stable.
Good. What would happen if you have a negative coefficient in the characteristic polynomial?
Sorry. Well, if we have a negative coefficient, where, teacher, in one of these?
In the characteristic polynomial, correct.
Well, we still have to do the table. A lot of times, I think you can tell if it's unstable, but I think it's always better to make the table just to make sure that the ones of this in this column are positive or negative.
Actually, that is not correct. That is one of the main hypotheses. Yeah, Aldo?
Yes, teacher. If we see that one of the numbers of the coefficients have a different sign, we know that it's unstable. It could be all of them positive or all of them negative, but no mix.
That is correct. So that is the first hypothesis. All the signs in the characteristic polynomial should be the same, and we shouldn't have any equal to 0. And then, if all of them are positive or all of them are negative, which is basically multiplying everything by -1, then we still need to do the table to verify stability. But if we find one in the coefficients that is negative, we already know that it is unstable. Okay, so you can avoid doing it if you find a negative coefficient in here. Okay, so that's the main takeaway. Don't waste your time doing it if you already see a negative sign. Okay, but your explanation was really good, Juan Pablo, and with the support of your team, I think it was really, really good. Okay, do you have a second example with one that is unstable? Yeah, perfect.
Okay, so here we did the same process as the first one. So, well, but this was on purpose unstable, so we can see here the changes in sign.
How do you manage to do it unstable on purpose?
Well, what I actually did, well, I used a calculator to find, well, the coefficients and to see if it marks as unstable. But in my experience, I found it more difficult to find a stable system than an unstable. Actually, I first tried by subtracting some coefficients, well, like 0 coefficient. And what most of the results I got is that it was unstable, so it wasn't that difficult. But I just want to make sure that it wasn't stable and it has this change of signs.
Okay, question to everyone. Can you think of a strategy to find one super easy? Either stable or unstable? Using MATLAB? I mean, I think we have done it.
It was like using the function roots and putting some coefficients.
That could be a possibility, and pretty much it's the same that any did to check where the poles are located by changing the coefficients, and then you check, and then you see it again and again. But how can you design it to be unstable or stable from the beginning? Can you think of a way?
If you write the characteristic polynomial as poles, like s plus
Correct.
3 times s
if you have it already factorized using the zeta pk, for instance, then then you guarantee from the sign that it is already stable or unstable. So you can say, of course. Good. Thank you, Eric. anyway, the way you did it, Denny, is perfectly good and acceptable. Okay, but I think use the tools that you have around. It's also good to because it's not always trivial to understand it. But really good. Please continue, Anya. Sorry for interrupting.
It's okay. Okay, so what we marked here are the sign changes, as the statement of Ruth criterion, Ruth Hurwitz criterion states, is that the number of sign changes of this first column is equal to the number of the roots of this characteristic equation that it's on the right half plane, as we mark here. So here we have that there are 2 roots in the right half plane out of the 6 roots of the system. So here, said, we can easily state that this system is unstable.
Yeah. Really good. Good. Another team who can help us to go for the gain range for stability and how to verify the second point of the presentation. Anybody else? No one else has the presentation?
As teacher.
Yeah, okay, please. Thank you very much. Please.
Just give me a minute.
Absolutely, no problem. Yeah, thank you.
Is it showing?
It's showing now. Very good. Yeah.
To calculate the range of the gain, we have to add the last coefficient, like A0 multiplied by K. That is the gain that we are going to calculate. And
quick question, Jorge. Sorry for interrupting.
Yeah.
Why is it only in that term?
Because it's the independent variable that doesn't have the S.
Yeah, but why doesn't we have K in any other of the coefficients and only in the independent term? What is the assumption behind it? Any idea? What is the assumption? Yeah. Why do we have K in here only in the last term and not in all the others?
Because normally when we want to get the final value for a transfer function, we divide the independent of the denominator and the independent of the numerator, no?
That's exclusively for the final value. That is correct. That is correct. However, what happens if in the numerator we have more than just a coefficient or just a gain? What happens if we have a transfer function in the numerator? I mean, we have zeros in the system as well. What will happen then? So this is correct as long as we have no zeros in the system. Okay, is this clear for everyone? Aldo, you were raising your hand. Do you want to say something more?
I was going to say the same as Eric said.
Okay, so, and sorry for interrupting again, Jorge. I will take over the presentation just for 1 second, okay? Can you see my screen now? So,
Yes.
Basically what we're doing in here is we have a denominator and a numerator, okay? And this is the transfer function that we're working with. And with the first thing that we did, we were analyzing if this is stable or unstable in open loop, okay? What we're doing now is what happens if we have a system in closed loop with, of course, a structure as we have been using with a proportional controller equal to k, for instance, and a feedback like this. Okay? But this result that you're presenting holds only if the numerator is a constant value only. Because then you would have a gain. Remember that in closed loop, G in closed loop was equal to k times the numerator divided by the denominator plus k times the numerator. You remember that we did this a long time ago? So the only way that this element is equal to k0 or any constant in the end, only adding to the independent term, is that n only has an independent term. If we have more, we will have k in more than one place. Okay, is this clear? So what you're presenting is correct, Jorge, but it's under the assumption that we have a transfer function that has no zeros in the system. Okay, please continue. Okay. Yeah, but it's good that you start putting things together. That's why I'm trying to come in the middle. Okay.
Yeah, and once done that, we use the same array as the to know if it's stable or unstable. Just put the whole coefficient like A0 plus A0 times K. And we can see that in the example. In the next. Right there, we got the A0 is 1. So A0 times K is equal to K. And in the last part where is supposed to be A0 is A0 plus A0 times K. In this case, 1 plus K. And we solve the same way as the other one. Just we have the K. And once we got to the S1, we're gonna need to solve to K. And we're gonna, in this particular case, we got a quadratic solution. So we got two values that one of them is impossible, is unstable, and we check that in MATLAB. And the other one is the real range of the gain. So it's always gonna be from 0 to the value that we got from K, and the value is 0.82. And in the next page is the diagram. There we have the last point of gain that is 0.8222, but approximately.
Perfect. And this is another way to verify exactly the same. So yes, Jorge, exactly. Very good. Yeah.
And in the unstable case, we didn't do the table because we already know that is unstable. So the range is gonna be all unstable. So we just put the root locus diagram that proves that we have two poles in the real.
And if you would do the table, you would notice that pretty much all the columns on the first all the values on the first column, you never find a K that fulfills that. So all of them are positive. So yeah, very good. But of course, if you have MATLAB in this tool, this is a super easy way to determine it, because it's simpler to do and analyze the root locus diagram than to analyze the the root Hurwitz criteria. Okay. Very good, Jorge. I love the way that you confirm with it. So very good. Yeah. Last question. Perhaps someone else can answer, and it's a super easy one. How would we know if the system is stable or unstable with a particular K, which is, of course, a consequence of what we have seen in here? Basically, I think you just substitute K and run the table again. That's super easy. I think it's even easier than solving it with K. Okay. But I have another question. What happens if what I have is a compensator, not a proportional controller? Can I use this tool to determine if a system in closed loop is stable or not with a particular PID or with a particular compensator, or with a compensator with a value of K non-determined? Can we use it or not?
Can you repeat the question, teacher?
Yes. Can you use the root Hurwitz criteria or criterion to determine if a system is stable with a particular controller?
I think so, because you're just adding the things to the characteristic polynomial, no?
That's completely correct. So basically what you do is make the multiplication of the controller times the plant, and then put it in closed loop, obtain that one in closed loop as the transfer function, and analyze the characteristic polynomial, and then you will see if it's stable or not. In many cases, you can even find a negative in the characteristic polynomial and say, okay, it's already unstable. I don't need to do more. But if everything is positive, then you just continue. Okay. Very good, Eric. Thank you. Okay. So how easy or how hard it is to make a quick research and to understand this topic? How would your experience now trying to do some research a little bit?
I like these types of activities, teacher.
Yep. I particularly don't like to go deeper into this topic because, first of all, it's easy. I mean, it's easy to follow it, to understand how it is. And second of all, we have another tools that we're using to analyze the same. Okay, and I prefer to devote a bit more time on that than to give you a huge example on this and see if you're good at solving a determinant or something like that, which I don't think adds much value. I prefer you to think and to analyze the root locus diagram. Okay, thank you very much, all. I really expected that all the teams had completed the work, but sometimes it doesn't happen. I also understand that. But from my point of view, the topic is well explained by everyone. I will say that this task is completed for the whole group. Okay, so the team who didn't manage to finalize, please buy a coffee for the other ones. Okay, that's the least I expect. Let me share my screen now. There is another activity that I want you to do, which is a quiz on the locus diagram. Okay, but to do that, I don't want you to just go now and do it. But there is this material that is called root locus. Okay, lugar de las raíces in Spanish. So it's a presentation that is in Spanish. Let's quickly go through it. Okay, it's a presentation that explains in a very detailed way how to draw the root locus diagram. Okay, it explains a bit on what is the rational function that we are trying to solve, how it is expressed, and how we'll make the analysis in the complex plane. Okay, I want you to read it and then answer the questions. The questions are not in the specifications on how to draw, for instance, some specific lines to follow the trajectory of the branches, but more on the general part. But please read this one and then answer the root locus quiz, okay? And I will give you the until next class to do it, okay? So let me just change the due date. It's an individual work, and this is needed to be completed October 20th, okay? The whole day. So, okay, let's change this from today. Good. So it's going to be able from now until next week. Okay. And with this, we have concluded the topic about classical controllers. Okay. So I would like to give you a quick overview of everything that we have studied. Okay. To see if we have managed to complete something both on the competences that I would expect from you right now, and on top of that about the content. Okay. So this is the way that I would like to do it. So if we go to the beginning of the class and we go to general information, you will see that there is the topics that we will study, okay? So first of all was an introduction to classical and modern control systems. We have covered already the classical part. Today, I will cover the modern control systems, okay? I think now we have a common language where we can talk about poles, zeros, characteristic, polynomial, stability, controllers, and so on, PIDs, compensators. I think we understand also what is the relation between a sensor and the output of a system, as well as the relation between the input and what an actuator needs to do to a system, okay? We have studied as well something on the differential equation models, how to get them to transfer function. And the next step will be how to get them into steady space model, okay? That's, as I told you, today we start, and we will work on that in the coming weeks. We were doing both some modeling and also some identification of the systems. So for the modeling, you were working on a presentation. I will review it. I think by now you have done also a peer review. Did you get a request from the system to do a peer review on that task from the system? Have you done that?
I haven't, teacher. I didn't see it.
Okay, let me see how that's supposed to happen, but I set that homework to have a peer review. So you should have an assignation. Let me see if I need to do something to trigger it. Okay, else I will verify it and check it. Okay. Then we started the performance and characterization of dynamical systems. Okay, both the transient state and the steady state analysis. Okay, and we also check what is the relation of closed loop poles and transient performance. Let's quickly stop in here and go here to see what we have done. So what we are studying basically right now is from a system. We said that we would obtain a mathematical model. In our case, we got a transfer function, okay? Next thing we will do is we're going to obtain a steady space representation that looks like something like this, which is a differential equation, okay? Only that A and B are matrix and not only constant values. And the output of the system is equal to C times X, okay? Once we have a transfer function, how can we get a transfer function? So one is something that we call modeling, okay? And what is the other route that we took? How else can we get a transfer function? Can you tell me? You did a script about it.
By comparing the input and the output. All right,
yeah.
Identification.
That comparison is actually called identification, okay? So that's what we have done. What do we use to do this identification? We use the analysis of the transient performance and not so much on the steady state, but mainly the transient performance and the characterization of the systems. Okay, that's what we use to do it. Of course, as well, something on the steady state. Okay. Now, the next question is, why did we use mainly only identification for first and second order systems? The main answer for that lies in the fact of the dominant pole. Okay, so the dominant pole can either be a pole on the real axis or a complex conjugated pair of poles. We can have more, but the dominant one, meaning the one closer to the imaginary axis, will always be either a real pole or a complex conjugated set of poles. Okay, and that is basically a first or a second order system. Okay, and you know how to obtain a transfer function from a step response. Okay, so that is the identification process, and that's why we only studied this. The rest are a combination of that. Of course, you can actually see maybe an output of a system that has this behavior, and on top of that, another frequency. So you can know that there is something more. But as good as we can make an approximation of it and that we capture the main components, it might even be possible that a system that looks higher order, we can control it by considering a second order model, up until some limits, of course, but it is feasible. Okay. We cannot expect a complete full performance according to our specifications since we don't have the full model, but yes, it is something that with some lack of fulfillment of the complete requirements, we can do. Now, then we started to see how the system behaves in closed loop. All this was done in open loop. Then we started to analyze the closed loop system. And then we said, okay, everything that we already know from here, let's reuse it. So we imported the characterization of the system. And we started to analyze how the system would behave in closed loop. And from the final value theorem, the stability concepts, and everything that we learned from the system in open loop, we started to say, okay, this also applies to the closed loop system. Okay, what we are doing in SysOtool, for instance, is we are adding artificially poles and zeros and creating a new system. So there exists another system that has that set of poles and zeros that mimic the same behavior as a system with a particular set of control or zeros and poles that come from the controller that we are trying to analyze. And then we just make the same analysis. And of course, for this, we were using different tools. The root Hurwitz, the root locus diagram, and there are many more. And of course, we were doing a lot of simulation and analysis. Okay. We talked about some main controllers, the proportional controller, the PID controller, and in the middle, we can also have a PI and a PD, which is pretty much something similar to both of them. And we can also have a compensator. Okay, and we said that there are two types, the lead and the lag. And we can also have a combination of both. And that this is the one that works the best in general. Okay. So with these general two strategies of control, because all of these can be categorized into the same type of control, and the compensators, we pretty much can do a lot of things on the system. Okay, improve the error in a steady state, reduce settling time, improve transient behavior, okay? So with this, we can determine a set of requirements to the system. Of course, also considering input limitation, output limitation, and with that, we need to provide a controller that fulfills a lot of requirements, okay? And you're gonna use all of these into your final project. But basically, we will talk about it in the next hour, okay? That we will see what you're gonna be working with, okay? So if we go back in here, we also studied some basic control actions. We didn't really study mathematically how the on-off control actions work, but we know by now that basically we will get a range of performance, but there is nothing that's following a particular set point. But then with PIDs, we can do something more than that. We studied the stability of feedback systems with root curve widths, how the steady state performance and the transient performance, okay? And we did some control based on the root locus design, meaning compensators and even PIDs designed directly in the root locus, okay? So what is missing for the rest of the part of the semester is the steady space control design. So that's what we're gonna start today in the second part of the class, just after we discuss the final project, okay? So if we take a quick map of what we have been doing, is this what we have been doing, okay? So you can do analysis for systems, and we can also do design of controllers so far. In the competencies that you have acquired, you can analyze a system in open loop and propose solutions to control it in closed loop and improve the performance according to some requirements, okay? That's what I expect from you nowadays, okay? But let's see now in the proposals for your final project, how we will tackle this, okay? So let me check how the teams are, and I will ask you to tell me how have you decided to work toward the final project. We said that we would use a hybrid model where you can either do something in simulation or you can also do something in practical with operational amplifiers, okay? And we can find a way to do it to make it happen. So there are two proposals that I can do now. We can have 10 minutes meeting per team. We have 4 teams, and we can start now with group 1, that is Jose Miguel Flores Murakami, Sasan, Juan Pablo Rivera, and Carlos Daniel. And then in 10 minutes, we meet group 2, that is Aitor, Jorge Andres, Alberto Javier, and Paulina. Let me quickly share my screen so you see it. Then group 3 in 20 minutes, and group 4 in half an hour. And then we meet all back together in approximately 40 minutes. So 50 minutes, so we have a 10-minute break. Is that a good idea, or do you want to listen what the other teams want to do? What do you prefer?
Your idea is okay, teacher.
Good. So then let's start with group 1 at 11. Group 2, 11:10. Group 3, 11:20. Group 4, 11:40. And then we all meet 11:50. Okay, after 10-minute break for everyone. Good. So you can leave or you can stay. Let's start with group 1. I will stop recording right now. Okay.
Are you going to send us to breakout room so our team can talk, or?
Basically, my idea was that you come in here and in here you present. If someone wants to listen, they